All right, everyone. So this lab is on capacitors and capacitance. All right, so in front of you, you have a picture of actual capacitors. So, capacitor is actually a device that is used quite a lot in electronic devices, for example. Every phone, every computer technically, can have a capacitor because one of the important thing about capacitor is it's a device that can store energy. It's not like a battery. Let's say battery can not only store energy, it can produce energy. Capacitor cannot really produce it or generate its energy. It can store energy and allow, let's say, devices to use some of the stored energy. But still, it's an important device because it can work as a sort of like a backup for let's say when the battery dies, right? The device can still use the capacitor energy for a while until, let's say, maybe your battery is fully charged or something like that. But as you can see, that capacitors are generally conductors, and they always you can see in this image over here, right? They come in different size or shape. They are uh, different geometry, right? There's a cylindrical, there's a spherical, and there's also parallel plate, and that is the one that we're going to be considering. So the parallel plate capacitor is the one that I'm gonna let's say, concentrate on doing this lab. And most of the time, that's what you usually concentrate also in your lecture classes as well. All right, so parallel plate is basically two conductors like this, right? That have same area A, so same cross-sectional area A. They are separated by some distance D. So let's say this distance D here is the separation. And let's say initially you can think of, like, let's say they both are neutral. So let's say when you have a capacitor that is uncharged, then you can say that none of the plates have extra charge, some kind of extra charge. That means that it has charges, but they're all equal amount of positive and negative, so they are, let's say, neutral. What we do here is, to charge a capacitor, we need to connect some kind of a battery or power source. So one of the things I want to talk about here, there, you can see the title, right? It says capacitors and capacitance. Now the capacitor is just this device. So that means any of those devices in the picture, or this parallel plate that I just drew on the right side. That's a capacitor, which is just the device itself. The capacitance, which we use C for that, then that will be the amount of, sort of like, let's say, energy it can store. It's not like a unit of energy, but sort of like, let's say, when we talk about capacitance, it gives us information about how much potentially we can store energy and things like that. Higher the value of capacitor or the capacitance of a capacitor, more energy it can more energy it can store. Now, how do we then, let's say, charge a capacitor? Well, we use a battery. So let's say I can draw a battery like this with a positive terminal and negative terminal, or I can start using a circuit diagrams. So circuit diagram is an abstract, picture, let's say, more like a pictorial representation of some kind of device. So for example, this is a battery, and the circuit diagram of the battery will be long line for the positive terminal and the shorter line for the negative terminal. So that's basically a battery, and I use wires to connect battery. So that's basically the circuit diagram for the battery. Now let's say what I need to do here is then connect the positive terminal to one of the plates. Let me kind of like do. So like, let's say one of the plates, that means the top plate, by the way, the plates are not touching each other. There's the gap between them. And right now we can assume that the gap between them is air. So right now there's air between them. So if I then connect the positive terminal to the top plate, and then the negative terminal to then the bottom plate, then I can technically start the charging process. Because one of the things happens right away when I make a full connection. Right now I have a closed circuit. So right away, there's an electric field in this circuit. All right, so the electric field starts from a positive plate and goes in this particular case, right? Because my positive terminal is right here and the negative is right there, it starts from positive outside of the battery and goes and then goes from one plate to another plate, right? So the top plate to the bottom plate, and then comes back to then the negative terminal. So this is my electric field. That means there is an electric field in in the circuit. Now, what does it do? What does the electric field do, and how does it help us to charge the capacitor? Well, if you remember, right, I mentioned that the capacitor has equal number of positive and negative charges on each plate when it is, let's say, neutral or it's not charged. It means that, for example, if I'm looking at there are like let's say one, two, three positive charges, and then one, two, three negative charges here, and then again one, two, three positive charges at the bottom plate, and one, two, three negative charges at the, also bottom. So that means the equal amount of positive and negative on each plate. Now, when there is an electric field, remember, electric field affects all the charges. That means right now, when there's electric field, it's gonna affect all those charges in the plates. Now, one thing, hopefully you guys already know this time when there's a electric field and electric field, let's say pushes or pulls, it usually affects the electrons, not the positive charges. That means the electric field in the circuits, right? Um, Even though the direction of the current we use as a conventional direction of the current, which you will see later on, is defined as the direction of, let's say, the positive charges that would be flowing. But here, think of it like this: if there's electric field, then it's going to affect the negative charges in your plates. What it means here is it's going to push the negative charge. So one thing we know here is then here's the equation: force equals charge times the electric field. So that's the equation that tells you if there's an electric field and you have a charge, there's going to be force on it. Now, because these charges, as I said, right, the affected charges are negative charges, so there's a negative there, which means the force acting on the electrons is going to be in the opposite direction of electric field, which means that this guy here is going to then be taken from this plate, be pushed in the opposite direction of electric field. So you can see, right, electric field is clockwise, then in this case, the force will be counterclockwise. So then that means this negative charge will be pushed all the way to the other plate. So then think like this plate now gains an electron, but the top one now lost an electron. Same thing, let's say, with the second electron. So this is going to be then pushed out, from top plate to the bottom plate counterclockwise. So this is going to be pushed from top to the bottom, going counterclockwise, which means now I have two extra negatives. So those two cancel each other, these two cancel each other, these two cancel each other. That means what I'm going to end up with is the bottom plate is going to have more negative than a top, than it had before, and that the top plate going to lose, electrons, so it's going to be positively charged. That means what I can say here is this: the top plate now positively charged, the bottom plate now is negatively charged, because I'm taking a certain amount of electrons from the top plate and moving them to the bottom plate, which means when I'm writing this plus Q and negative Q for the top and bottom plates, it's exactly same. That means plus Q for the top plate is exactly same as amount of charges for the bottom plate. Why? Because, you know, I took, let's say, 100 electrons from the top and moved it to the bottom plate. That means how much change in electrons I have is exactly equal for the top and bottom. So that's why the plates always have exactly same Q. That means if it's this is one capacitor, that means this capacitor have exactly same amount of charges on each plate. It just one is positive, the other one is negative. All right. Now, that means in this particular case, what we have is this. Also, before we, let's say, started charging, this V here is a voltage of the battery. I'm put like VB. initially when the capacitor plates were not charged, voltage for that capacitor, which is then potential difference, right? Potential difference for those capacitive plates was zero. This is, you can say, at t equals zero at the initial time, right? There was no potential difference between those plates. Why? Because, they were uncharged. But as soon as we connect the battery to the top plate and the bottom plate and start moving the charges, then the potential difference between them starts increasing. Now, let's say the battery has a 10 volts, this is the voltage of the battery. Okay. So the capacitor has no potential difference between its plates in the beginning. But as you start moving more charges, more charges, more charges, then this, as a function of time, voltage across capacitor starts increasing. There are two reasons for that. One, because you are moving more charges between, top and bottom plate. Plus, as you start doing that, the electric field between the plates starts increasing. Now you have higher, greater amount of electric field line going. And what happens here is then the voltage of the capacitor going to increase until eventually it matches voltage of the battery. That means when the voltage across capacitive plate, that means potential difference between top and bottom plate, is exactly same as the potential difference between positive and negative terminals, which is the voltage, that's what the voltage of the battery is, then your charging stops. That means you can say your capacitor is fully charged. All right. That means one thing we have here is this. Let me do another diagram a little bit cleaner. So let's say this is VB, 10 volts, positive plate, negative plate. So then this is my capacitor. Again, I'm gonna do let's say a circuit diagram for the capacitor. So the circuit diagram is generally two parallel lines like this. Okay, so this is a circuit diagram for the capacitor. But let me just for now, I want to do just plates like this. So then I can also talk about some of the other things that capacitance depends on. Okay, so that means once we start charging, then we can say eventually I'm going to have the top plate to be positively charged and the bottom plate negatively charged. And then I can say then this plus Q and minus Q are exactly the same. So now if when the voltage of the plate, right, VC means the voltage of the capacitor, that means the voltage between its plates, matches the voltage of the battery. So you can say this is fully charged. Okay. So fully charged means then electric field is now zero. That means there are no more charges moving from one plate to another. That means it's fully charged now. Okay. So that means our goal is more or less whenever you're charging a capacitor, right, is to charge it until the voltage, you know, exactly the same between plates and the battery. Again, then question is how do we know that, right? Well, it's easy for us to know because there's a device called a voltmeter. So the voltmeter allows us to measure the potential difference between 2 points. It has two probes. So if we take one probe and let's say connect it here, and the second probe connected over there, which is, well, actually connected here. See, I'm measuring the voltage of the battery. And what I will see here is this 10 volts. And if I move this voltmeter and I put it here and do the same thing, right? Measure this plate and measure the other plate, I will also then measuring voltage of the capacitor. Let's say I will get the 10 volts. Then I know that this is fully charged. Okay. Now, when you're charging a capacitor, that usually takes about no more than a few seconds. So it's very fast process. So that means when as soon as you can make a connection to the capacitor, connect battery to the capacitor, the charging process takes like sometimes a fraction of a second. So that means right away you might see that voltage of the capacitor is basically already matches the same as the battery. That means if it's 10 volts, this is 10 volts. If the voltage of the battery, let's say 1.5 volts, and this will be 1.5 volts, and so on. That means it will match exactly the battery voltage. Then we can say the capacitor is fully charged. Now, how about this quantity that we call capacitance, right? So what is that? So how can we calculate? Well, there are two ways we can calculate that. One of the ways is calculating the potential or measuring the potential difference between the capacitor plates, and then finding the amount of charge that we moved. That means, the Q, the amount of charge, divided by V. So that's this ratio Q over V is then also equals, exactly the capacitance. So the units are coulombs per volt, but we define this to be farad, F for the farad. So this is basically the units for the capacitor. So the capacitance can be calculated as a ratio of the charges divided by the potential difference between the plates. So the charges accumulated on the plates divided by the potential difference. So Q over V. Now, interesting thing about this equation is that the capacitance value is actually a constant value. For example, the question is this: what if I have, instead of, let's say, 1.5, what if I do, like, let's say, 3-volt battery? What will happen if I do 3-volt battery instead of 1.5? That means I'm doubling my, let's say I'm doubling my voltage, right? Well, what happened here is that in the circuit, you're going to get double the, electric field magnitude, which then move twice the amount of charges. So then your charges will be double. So then you can see, right, that the effect cancels out and you have the same Q over V. Well, what if I make this now 30 volts, which is, 10 times what it was before? Well, then you have, this one is then becomes 30 times. That means what you're doing here is, if you're changing, for example, voltage 30 times, then charges also change 30 times, and, exactly same effect. That means, they're proportional in terms of when you change one thing, the other one changes exactly same amount or by same factor. That means the C is always a constant value. Okay. So that's why sometimes we can say that capacitance is technically a constant value, and it is independent of how much voltage or thing like that you have. So one of the things we're going to see is that once I charge and I, let's say, remove the battery, I can, still calculate exactly or find exactly the same capacitance. But this time, to find the capacitance, since I no longer have a battery, let's say, connected to that, then what I can do here is I can look at the area of the plates, and then the distance between the plates, and use that equation to, use those parameters to calculate the capacitance. Because the capacitance of a capacitor is directly proportional to the area. That means bigger the area, bigger the capacitance. So that means if I make the area bigger right now, well, the capacitance will increase. If I make the area smaller, the capacitance will decrease. So that means what I have here is the capacitance is directly proportional to area, but it also inversely proportional to the distance between the plates. That means if I move the plates from one another or bring them closer, capacitance affected by that. But in such a way that if I move them further apart, capacitance decreases. Move them closer, capacitor increases. Okay. All right. So going from here, proportionality sign to equal sign, then we can introduce a constant, and that constant is epsilon naught, which is permittivity of free space. So the equation becomes epsilon naught A over D. So this is then the equation of a capacitor that has air between the plates, where the epsilon naught, by the way, I can write two different ways. It's pretty much the same thing. There's two different notation that I sometimes use. So this is 8.85 times 10 to the negative 12 meters squared newtons times coulomb squared. That's just a electric constant. Okay. Now let's summarize this. That means what I have here is this: I have a capacitance of a capacitor that I can calculate using the charges over the voltage. Okay, so this is one way of finding that. But there's another way we can find that, which is basically finding that capacitance can also be calculated from this geometry. That means, from its area and then the distance between the plates, and then this is based on some kind of constant. That means this is the equation that technically we're going to be exploring in this experiment. That means we can see two things: capacitance proportional to area, directly proportional to area. So we're going to do an experiment to verify this. That means if I have a way of measuring and changing area, can I see then increase or decrease, you know, proportional increase or decrease in capacitance? And if I have the distance that I can change, am I going to get the inverse relationship for the capacitance? That means if the distance increases, will the capacitance decrease? Okay, that means those are the two things we're going to be exploring. All right, so on top of this, there's a third parameter we're going to be exploring, and that is basically this. So let's say if I have a battery connected to my plates, let's say something like this, right? Okay. So positive terminal, negative terminal. So think like this. Is there another way we can change the capacitance? So that's going to be another question. The answer is yes. Remember, I said that we start with air as, or vacuum, we can say air or vacuum between the plates. Okay. So what if we have something else, some kind of other material, insulating material between the plates? So that's something we're going to be exploring as well. So it is known as a dielectric. And the dielectric is a material, some kind of insulating material that we can insert between the plates. And one of the things we're going to see here is generally, this material, when you insert between the plates, changes the capacitance. And we're going to do an experiment to see how does it change. All right, so generally what happens here is this. When we insert the capacitance insert the space between the plates of the capacitor with some kind of dielectric material, then what we're doing here is we are changing the electric fields inside. So changing, some of the electric field that we had, let me do a different color, between the plates. And you're going to be able to also see. So today's experiment is basically actually a simulation. So it's very nicely demonstrates all of those things. That means once I insert the dielectric, the amount of electric field lines that I had before actually going to decrease. So one of the things we're going to do here is this. There's a equation that relates voltage and electric field. So if this D represents distance between the plates, and let's say voltage, remember, of the capacitor eventually going to be equal to voltage of the battery. So then I can find the electric field between the plates by using this equation. So it's voltage divided by D, V over D. Okay. So now that means V is equals to E times D. V equals E times D. Think like this. If the electric field changes, but the distance between the plates doesn't, you can see, right, then voltage also changes. And that's one of the things that we have about this dielectric. Also, this dielectric, when you change or you insert it with some kind of, the capacitor inserted with some kind of dielectric material, it actually has property that increases the actual capacitance. That means, for example, let's say C prime is the previous capacitance, where I had, like, let's say the distance between the plates filled with air. Then this, or thing like this. So I'm going to put like C naught. C naught is the original capacitance of a air filled capacitor. Then this C prime is going to be the new capacitance. And one of the things we're going to see is that it's going to be then increasing by this amount of what we say kappa. So this kappa is the dielectric constant. And dielectric constant has no units. It's just a number that is greater or equals to 1. So you can see, right, if the kappa is 1, then new capacitance is same as old capacitance, which means that we're dealing with the same, air field, a capacitor. That means kappa equals 1 is basically air or vacuum. That means anything else is going to be higher dielectric. So we can have a dielectric constant, for example, 5. So that means if I come back and replace this kappa with 5, That means you can see, right, new capacitance is now is five times the old capacitance. That means it increases by 5 times. There are capacitor, a dielectric constant or dielectric material that have a, capacitance of maybe 50. That means you're increasing it by 50 times. That means this is an easy way without changing the geometry of the, let's say the capacitor itself. We can change the capacitance by just simply adding, some kind of insulating material between the plates. And this is also something that we're going to be exploring. That means if I have a, so this is the equation, C is equals to, like, let's say C prime now, right? Is, remember, it's a kappa times the original C naught, right? So that means it's kappa epsilon naught, let me do kappa. So kappa epsilon naught A over D. That means you can say that this is then the general equation for the capacitor, where kappa equals 1 is air-filled capacitor, kappa equals 5, maybe Teflon or something like that, right? That means, this is just sort of like, let's say, our general final equation for the capacitor. That means we're going to explore three things. What happens with the capacitance when we change the area, when we change the distance, and then we insert it with some kind of dielectric material. We can see then what happens to all of those things. Now, in terms of then, let's say we talk about energy stored in the capacitor. Okay, so there's also, as we talk about, right, there's energy stored in the capacitor. It can store energy. And then let's say, how can we calculate that? So most of the time in our simulation, you don't have to do this calculation because it technically, allows you to measure it. Just basically it's a, allows you to calculate that. But it's important that you guys know that U as a energy of the capacitor is equals to 1/2 Q squared over C. So there's one of the equations that you can use, or it can also be Q times V over 2, which is the charges of the plates divided by the voltage between the plates. You know, it can also be written as C times V squared over 2. It's three different ways of writing the potential energy of the capacitor. All right, so hopefully this was helpful for the theory. Let's go back. Let's go now to the lab itself, so then I can show you like what's going on, what we need to do. All right, so here's the lab, capacitors and capacitance. So the learning objective for this lab. So in this experiment, you will investigate fundamental properties of capacitors and circuits involving capacitors. All right, so it's a nice simulation that you can open on your browser. So you can see right here's a parallel plate capacitor. Okay, so this simulation allows you to make changes to your capacitor, parallel plate capacitor. Make the area bigger, make the the distance larger or smaller, um, insert a dielectric and things like that. And even you can do like multiple capacitors, which we're not really doing in this. All right, so you're going to be able to, let's say you start with some kind of pre-lab assignment. So one of the things we have here is, so there's a pre-lab, a few questions that I hope you should be able to kind of like answer them as we go. So, and then you lock your questions, like your answers. So the section is locked, you cannot go back. That means just watch the, let's say once you watch the theory part, right, of this lab, you should probably be able to answer, most of these questions that I have in this lab. All right, so you lock it and then you can go to the next one. So here's A1, which is changing area and predictions. Okay. So as you can see, right, so here I have, let's say, the simulation, and go back. Okay. So, and I have, let's say several parts where it basically shows you what you need to do in order to make measurements and things like that. So you can see, right, so we begin with our capacitor fully connected to the battery. So like I'll give you a picture of what you need to do in order to, let's say, before you make measurements, set it up so that you can then start making measurements. That means, this is what I expect you guys to, do in order to, let's say, charge. So it gives you a picture and asks you, some questions. And again, based on what you just learned, right, in a lecture class, or also in the pre-lab lecture, you try to answer some of these questions. Okay. So again, this is basically we're not making any measurements or anything like that. This is just basic questions about capacitors. So like, let's say based on the pre-lab lecture. All right. So this is basically your prediction. That means what will happen if you, let's say, increase the area, decrease the area, and all of those things. Then we're gonna, log this after you answer them. Okay. By the way, for example, some of them have two submissions. So that means, if you get it one time wrong, you can then get, try again. Some of them have, one submission. So that, they're not worth much, right? They're about 1 point each, but, you know, you want to like think about it a little bit and then, answer them. Here's then what we're going to be doing. So this is basically, data collection and analysis. So in this section, you will be using the simulation to collect the data to show how changing the area of the plates affect C for the capacitance, V for the voltage, Q for the charges, E for the electric field, U for the energy. It means all of those, parameters we want to, explore. How will they change if we change the area? All right, so that means we have two, different scenarios. Capacitor connected to battery, where we will charge it, right? And then the capacitor is charged and then disconnected from the battery. So this is to show you what you need to do in order to, let's say, you know, connect it to the battery. That means, this is basically what you should look like. The screen should look like this. Okay. So then here's our simulation. So then here you will be able to load the simulation. It takes a little bit, maybe like a half a minute or so, but it will load it. All right. So this is pretty much what we have for the simulation. So you can see, right, you have a battery and a parallel plate capacitor. So for example, then I can increase the, so for right now, this means that battery, is zero. So it's a zero voltage. So moving it up gives us 1.5 volts. And it gives you the direction in which, electrons are moving. Remember? So as I said, right? So if you have a, voltage of plus 1.5 or something like that, then electric field, you can see, right? Here's the electric field, which goes clockwise, right, in your circuit. Then it's going to move the electrons. You can see, right, as you're charging, your electrons, move and move and move. Your electric field increases until, let's say, you're fully charged. Okay, so one thing I can do here is I can, have a way of measuring capacitor, plate charge, stored energy, and here's a voltmeter. See, if I take a voltmeter and connect to the, terminals of the battery, all right, I can connect it right here, doesn't matter. So, and it's 1.5 volts. So that means, I have 1.5 volts. Now, how about if I make the same measurements about for the parallel plate capacitor? Again, 1.5 volts. Okay. That means, for example, now, uh, see, when this is zero, the other one is zero. So it's not charged. But as I start charging, so it starts increasing until, it's fully charged. Okay. That means this is, one of the things you're going to be doing. And battery connected, so I'm going to give you this. So that means, let's take then the area. You can see, right, uh, area here, 100 meters, 100 millimeters squared. So then what you need to do here is make measurements with this area. Okay, that means the data table tells you, okay, so here's the area and here's the distance between them, right? Which is, 100 millimeter squares, sorry, 10 millimeter. So what is the capacitance? So the capacitance you can see, right, this green bar. So it's 0.89 times 10 to the negative 13. That means you just basically write it down in terms of picofarad. So convert that into picofarad. So, basically it will be 0.089 picofarad. And then the voltage. So that means, for example, so this will be, 0.089 for the capacitance because it's 10 to the negative 13. Pico is 10 to the negative 12. So because it's 0.89 10 to the negative 13 becomes 0.089 10 to the negative 12, which is what pico is. Voltage is 1.5 volts. Now charge. What is charge? Again, that's the red bar over there, which is 0.13 times 10 to the negative 12. That means it's already in pico. So 0.12, no, 0.13 pico. So then we go to the next one, which is electric field. Now, what is electric field? Well, it doesn't show you electric field value. But remember, I give you an equation for electric field. So then you can say, all right, so I'm going to have, you click here, those three dots, and then you go say, okay, change column formula. Electric field has an equation where electric field equals voltage over the distance. Remember, I gave you that. Let me use a different color. So electric field equals voltage over the distance, which means here you can say, all right, so I'm going to take my voltage and divide it by distance, and this will be formula for my electric field. You click on that, and that value you already see is then the electric field. Potential energy. Well, we don't need to calculate potential energy. It's given right there as a yellow bar. Okay, which is 1 times 10 to the negative 13, and as a pico is 0.1 times 10 to the negative 12. All right, so this is what you do. So this is for the 100 millimeter square area. Then what you do here is you change the area and then measure the same thing again. And the way to change that, you can see, right? Here's this arrows over there, right? So you can then change it to, what do we want? We want 400. That means we take this and we move it to 400. There you go. Now it's 400. And then we see what changed. Well, what I have here is, look at the capacitance. Did it change? It did indeed. How about charges? Well, you go back and compare. My charge is 0.13, and here I have 0.53. That means, yes, it definitely changed. Energy definitely changed. Voltage didn't change. So voltage didn't change. So that means in this particular case, you can just write those things down. All right. So, and use that to answer some questions at the end. For the second table, it says battery disconnected. That means what we do here, we click this disconnect battery, and then now the battery is disconnected. Okay. And then basically repeat the same thing. Okay. So that means go back, or if you want, you can just reset. But the idea here is that you go back like this, and then you measure everything in terms of what you had before. Okay. So again, so basically charge it, right? And like this, and then disconnect, right? And then make some measurements. So that means you do the second part, and then compare to see, let's say, what's the difference, what changes, and things like that. And then everything else, simply just looking at your measurements that you did for those two different conditions. All right, so then you can just basically do that. And then here it says, well, we will disconnect the battery. That means this is for that second table. So then you disconnect, and then make some measurements, and then here answer some of these questions in terms of, let's say, what happened, okay, when you disconnect it. So the above questions, for example, right? So this is 5 and 4. This is for the the first table, battery connected, and then here you then disconnect and then answer the next two questions based on what you observe. Okay. All right, so like the answers, go to the next one, which is changing the separation distance, which means you're basically doing the same experiment in a way, right? So, you're charging capacitor when it's battery connected, and then, disconnect. But this time what we're doing here is we are going to be changing the distance between them. Again, some preliminary questions here. So you just answer some of these questions based on, some of these images that you see, and then basically pretty much your prediction, right? So let's say, for example, predict which of the physical variables listed below will change when you change the separation distance. Recall what we talked about right before. So let's say when you change the separation between the plates, what quantities will then be affected by that? So in which direction, let's say, the electron will be traveling and all of those things. Once you make your predictions, like your answers, then go back, and then we're going to then do the experiment to verify if you predicted that, correct or not. That means this time around, what we have here is, you can see, right? So you have, again, in terms of capacitor charged and, and disconnected, then capacitor connected to battery. That means you first charge it and then disconnect and then make measurements and then, connect it to the battery. So this is basically charged and disconnected. That means your setup should look like this when you make some measurements. That means, again, you wait until, it opens up to make measurements. All right. So again, how do we charge this? Well, you press, you go from 0 to 1.5 volt, right? Let's say, and you should then charge it. Okay. So you charge it and then disconnect. Remember, so kind of, we're referencing that first image, right? So we want it kind of like, charge it, and then here, oh, sorry, this one. So we want this type of image. So you charge it and then ready to go. Okay. So then from here, what we do is we, let's say, set it up like this, and then we can make measurements. Area is kept constant. That means 400. That means technically what we need to do here is, so connect it back, make the area 400, charge it, right? And then disconnect it. Then what I have here is this. So there are two distances, 10 millimeters and 5 millimeters. So right now it's 10 millimeters. That means, what I need to do is write down the capacitance that I see. Again, so for the capacitance, that green bar. For the voltage, voltmeter. For the charge, the red bar. For the electric field, that equation. And for the potential or energy, the yellow bar. Okay. Sometimes when it's, let's say you can't really see well, you can just click this one over here and then, it will kind of give you that. All right. So similar things then, right? So you measure all those things, write them down in the table. Okay. So, and then come down and answer question, and then go, and part 5, it says now connect the battery. Okay. Then go just basically connect the battery, right? And that means, again, I give you the image, what it should look like, and then make a measurement and things like that. And the way we would change the distance, right? Just basically this arrow here, you can just move it, closer, let's say further, closer, further, and things like that. Okay. And then you want to see what happens to the capacitance when you're changing the, distance between the plates. Okay. Again, write down the observation, the measurements, and pretty much answer some of those questions. All right, so once you're done, you like that, you go to the next one, which is adding dielectric. And remember, dielectric is a material that we use, as a, instead of, like, let's say, air between the plates, to increase the let's say, the capacitance. Again, so we will, have a capacitor charged and disconnected from battery, and the capacitor connected to the battery. Okay, that means this is what you need to have as a condition, right? You can see, right, you have plus minuses on the plate. That means it's already charged. Then you insert the dielectric. So there are, you can see, right, air has a value of k equals 1, and then there's a bar over there, right, that gives you from 1 to 5. That means, again, answer some of the preliminary questions based on the, the pre-lab lecture and some of the knowledge that you have already on this, and make predictions like this, and go and answer, to verify that in the experiment. Again, so this is, one experiment that you do, which is charge it, then disconnect from battery, and then make measurements. And the other one is basically connected to the battery afterwards, so, which is basically something like that. So you have image of both of those in order to do measurements. All right, so let's see what we have here. All right, so in this case, what we do, you can see, right, the simulation itself has several tabs. So we go from introduction to dielectric here. So, and you can see, right, you already have a material there. So here how we can change the dielectric constant to anything we want, for example, or it can be like, let's say something specific. Say Teflon is 2.1, paper is 3.5, glass is 4.7. So let's say here we're doing custom, so we're going to do 1 and 5. So kind of compare what is, like, let's say air compared to something that has a dielectric of 5. So again, what we will do here is we charge it, disconnect, right? So that means that's what we're doing. So you can see it already pre-filled. So area 100, distance is 10 millimeter, dielectric 1. And then what we do here is, let's say we have those information, right? So we take it. So let's say if I put the voltmeter here, I get 1.5. Remember, so that means because it was voltage of the capacitor same as voltage of the battery. But then I insert this in between the plates and then see what happens there. So you can see, right? So technically, you write down the measurements and you can see, right? Not much happens. Why? Because, the dielectric constant is 1. That means it's basically the same material as it was before. Okay. But if I go back and change the dielectric material to, let's say, 5, then when I do that, everything changes. Okay, everything changes. So that means you're going to have to basically make those measurements. You can see, right? Capacitance changes, energy changes, voltage changes, but one thing at least remains constant. One thing remains constant, and then you can then basically play around and find out what remains constant, what changes, how they change. Did the capacitor increase or decrease? Did the voltage increase or decrease? And all of those things. That means this table then allows you to do that, right? So look at the electric 1 compared to 5, make those measurements, and then compare them. And at the end, battery connected, which basically just click on this, connect battery, and then, write it down and all of those things. That means measurement when the battery is connected, and, which is basically, again, the image is given here. And then the last question is basically, kind of like, check your prediction, explain any deviation from your observation. And then, like an answer and continue. Basically, this is pretty much the lab is, you're going to have a submit. Mine is just basically instructor version. All right, so that's pretty much it for this lab. So you can see, right, it's a nice simulation, allows you to see, measure, observe the capacitance value when you change some of this geometry, right? Area, distance, and or have a dielectric constant between the plates. So, all right, so um, start working on it a little bit earlier because it's, as you can see, probably will take a little bit of time. And if you have any question, just shoot me an email.